As for the math part, we'll have to recall what we learned in senior high school when we attempt two equations of final velocity for respective two balls in elastic collision using conservation of momentum and conservation of kinetic energy. I put the two equations in the yellow box on the right top side. So in our case here, two balls will drop at the same time with the same velocity v, and the bigger ball will drop to the ground first. Then the smaller ball will thus have a velocity 2v relative to the bigger ball, because the bigger ball will then have a velocity minus v. So now go back to the equation. We plug in that mass of the second ball is smaller than the mass of the first ball. Then we can get the velocity, final velocity of the first ball equals to v, and the final velocity of the second ball is 3v. And then using the physics equation that velocity squared equals 2 times gravity times height, we can get the conclusion that the height of the second ball will be 9 times the height of the first ball. Now let's look deeper. We analyze the situation using two connected springs with mass m1 and m2. If the two balls are in contact, in other words collide, when incident at speed v0 and also in contact during the collision with the end stop, then the situation can be analyzed by this graph. I put it in the downward side of this page. These springs can only be compressed instead of extended. We use spring 1 and spring 2 to simulate the process of collision respectively between ground and M1 and environment 2. You can see when the first ball drops, the downward side is deformed, so we have to put a spring here to represent it. And when the second ball collides with the first ball, both the downside of the second ball and the upper side of the first ball is deformed. That's why we also have to put a spring between the first ball and the second ball. And also from the graph, we can see that x is the coordinate of the center of mass of M1 and y is the coordinate of the center of mass of M2. In which case, the compression of S1 can be equated to x, and the compression of S2 is y minus x. While the springs remain compressed, we can write the equations of their motions as the upper two equations. I put it in the left, where F1 and F2 refers to the forces on each mass. By Hooke's law, we can also write force F equals spring constant K times displacement X. Also, you have to add a minus sign. Then by Newton's law, we write force equals mass times acceleration, which is twice differential of displacement. We now discuss the influence of the ratio of mass and the ratio of spring constant. Let's see a single case first. This is a case in which m1 over m2 equals 2 and the spring constant k1 over k2 equals 20. In the time interval 0 to 5 milliseconds, we can see there's a first event, which is m1 collides with the end stop. Move on to 5 to 19 milliseconds. We see the second event that there's a slow collision between M1 and M2. We can observe that where there is slope, there is a change in velocity, which indicates a collision. In this page, this graph shows the rebound speeds of the two masses as a function of ratio, a spring constant for three values of the mass ratio. If K1 and K2 are similar in magnitude, the collisions of M1 with the end stop and with M2 can no longer be described as separate events, which is in the left side in our graph. You can see that the lines are all sticking together. And in order for mass M2 to rebound at high speed, the ratio K1 over K2 needs to be comparable to or greater than the mass ratio. You can see that the right side in our graph, they can be separated into two events, and the velocity is very high.